Hey everyone, as always, hope you're doing well. This video is 6.4. We also do 6.2 and 6.3, but I personally like to do 6.4 first. So the last video you probably should have watched was 5.5, and now we're doing 6.4. These are polar equations. Now we won't get very far into the actual equations part of this. Really more what we're going to be doing is talking about polar coordinates. So let me kind of explain what that is. So an XY point is called rectangular coordinates. Or sometimes they can be called Cartesian coordinates. But they're just graphed on like the normal XY plane that you've seen for the most part in your life. Polar coordinates define points by a directed distance and some angle. Really what we're going to see is that polar coordinates are in this form. The directed distance is going to be an r value, and then the angle is going to be a theta value. So we're going to write these as r comma theta. So instead of writing xy, we're going to write r and theta. And so let me kind of draw this a little bit just to kind of show you what we're going to be working with here. So this is called the polar axis. And you'll have some point P. This over here is going to be called your pole. And so the size really of like how far out P is, that's going to be your R value. And so this point here is going to be an R comma theta value. And the theta tells you, how far that angle is going. Okay, my hope is that when I write these equations for us, it's not going to feel new to you really at all. So we're doing something like new as in like it's used for something different, but all the equations that we're about to use that I'm about to write down are all equations that we have seen before. So we have this formula that cosine of an angle is equal to x over r. This leads me to saying that x is equal to r cosine theta. I also have a relationship that sine theta equals y over r. This tells me that y equals r cosine theta. These two equations are going to be used whenever you want to go from polar to rectangular. So with these, you're going to be given r theta, and you're going to have to find the xy point. And those should look extremely similar to the equations that we used in 5.4. The only difference is in 5.4, I called it Vx and Vy because it was for like a vector, but not actually anything new. Oh, sorry, I wrote something incorrectly over here. I accidentally wrote cosine there, and I should have written sine. Sorry about that. Because I was manipulating this equation and I just accidentally wrote cosine instead of sine. Then we want to talk about what if we need to go from rectangular to polar. So what if like I have x and y, but I need to find r and theta? R is equal to the square root of x squared plus y squared. That comes back all the way from 1.4 and 1.5. And we saw it again in 5.4. Now theta can be found in some different ways. It depends on what quadrant you're in, like which one might be beneficial. So theta, you could use tangent if you want. And tangent is y over x. You could use sine if you want, which is y over r. Or you could use cosine if you want, and that one is x over r. So you can use any of those. It just depends on the quadrant that you're in, like which one will be beneficial. Really the same stuff that I talked about in 5.4, we're just using it for something different. So in these, we're going from rectangular to polar. So before I start like an example where we do like um, manipulating them from polar and rectangular and stuff like that, I just want to show you how to graph these. So example 1, let me go ahead and graph. So we're going to graph the following points. And these are going to be polar points. So first one we'll do 2 comma 5 pi over 6. B, let's do negative 3 comma pi. C, we're going to do 1 comma negative pi over 2. And then D, we're going to do negative 1 comma 450 degrees. So you'll notice that for some of these, I have the angle in radians, and sometimes I have the angle in degrees. So when you graph these, you're graphing them more on like a circle type like graph. So let me go ahead and I'm just going to draw a graph for us, and we're going to plot them all on the same graph. So the way this looks, the polar graph, if you want to go out by a radius of 1, that's a circle with radius 1. If you want to go out to a radius of 2 or r of 2, it's a circle in the center with a radius of 2. If we want to go out to 3, that means we're dealing with a circle of radius 3. And remember that all of these points that we're going to be looking at are r comma theta points. And I'll remind you of our angles. So this is 0 or 0 if it's radians or degrees. This is pi over 2. This would be pi. And this would be 3 pi over 2. So it's like you're looking at circles instead of like a well, it's a little hard to say, but instead of like an XY plane, you're looking at circles instead, circular shapes. So first, let's do part A together. I'll go ahead and do this one in green. I always think it's good to plot the angle first, and then you'll just go out by however far the R is. Be careful though, that R is a directed distance. So we're going to have to keep that in mind because it's going to matter if it's positive or negative. So 5 pi over 6, let's go ahead and figure out where that is. Remember that pi, if I multiply by 6 over 6, I can write this as 6 pi over 6. So 5 pi over 6 is going to come right before that. So 5 pi over 6 is something like here, but we only want to go out by 2. I didn't mean to erase that comma. So 5 pi over 6 is like here, and then I'm only going to go out by 2. So there's my point. So I didn't need the rest of the line. Oh my gosh, I did not mean to have the eraser on. All right, there we go. There's my point. So this is the point 2 comma 5 pi over 6. And so I know it almost looks like it's like a negative 2, but it really just means that when it's a positive 2 like that, it really means that the angle, like we went out by 2 at that angle in that same direction. Let me show you with part B why I'm saying it that way. So part B, if we look at pi, it seems like maybe our angle would be, like our point would be right here. Because it would be, okay, we go out, oh my gosh, this is killing me. Using this eraser. So usually we would go out by pi and we would say, oh, okay, we're going to go out by 3, so the point must be right here. The issue with that is that it's a negative 3. So actually we're going to go the opposite way. So it's like we thought we were going to go this way by 3, but we're not. We needed to go the opposite way because it's a negative 3. So this point for part B is actually going to bring us over here to this 3. So it's because we were originally looking this way because that's where pi is, and we thought we would go out by 3, but since it was a negative 3, we had to switch directions, so we had to go the opposite way. So instead of going out to the left, I actually had to go out to the right. So this is the point, negative 3 comma pi. If it had said positive 3 pi, that would be over here. Because it would have meant to go in the same direction as my angle. Let's do part C. 1 negative pi over 2. Negative pi over 2 is going to be down here. So I'm looking this way, and I want to go out to 1. So that's going to put me right here. So this is the point 1 comma negative pi over 2. And then this one we have another negative R value in there. So 450 is large. It's kind of hard to plot. Remember, you can always use coterminal angles to make angles smaller. So I'm going to subtract 360 and I get 90. So that tells me to go this way, but then it says to go -1. So actually, scratch that. I need to go downwards. I need to go the opposite way. It actually ends up as the same point. As part C. So C and D are actually the same point. I want to talk about part B a little bit more. Another way we could have written that, we could have said, okay, I want to go to 0, and I just want to go out by 3. So I could have also just called it the point 3, 0. And funny enough, that's also what it would be in rectangular coordinates. It would be 3, 0. So that's just another way we could have written that one. More common than not, so like most of the time, your R's are going to be positive. I'm showing you how to just graph them and stuff, so I'm showing you some negative R's. But when you find R, usually you're using Pythagorean theorem to do it. So you're going to get a positive R value. So we'll keep that in mind as we actually do some problems. So let's look at some problems where we actually convert these. So we're going to say, I'll say part A, we're going to convert the point 6 comma 210 degrees into rectangular coordinates. And I'll leave some space. Not sure how much I'm going to need. I'm going to leave a good bit. For part B, I'll say convert the point um, I want to pick a good one. I always like to do some where maybe you do have to use a calculator and some where you don't. This one, I would say leave your answer exact because you don't need a calculator for this one. 210 has a reference angle of 30 degrees. So there's no reason to use a calculator for that. This one, let's see. Let's do square root 3 comma 1. And I want to make one of these negative. Let's do this one negative into polar coordinates. And this one, I'm also going to say leave the answer exact. And I might make another one as well, of one where you do have to use the calculator just to show you how that would look. So for part A, I'm being given something with an angle. So that means I'm being given r and theta, and I'm being asked for rectangular coordinates, so I'm being asked for x comma y. So I'm going to use my formulas. I know that x is equal to r cosine theta y is equal to r sine theta. So I'm just plugging in. So x is equal to 6, and then cosine of 210. So 210 has a reference angle of 30 degrees. It's also always helpful to go ahead and graph these. So 210 is going to be in quadrant 3. And this is basically saying that we're going out by 6. So like if we graphed it, there'd be 1, 2, 3, 4, 5, 6 circles there. I drew that so horribly, but that's the idea. So 210 has a reference of 30 degrees. That's because that's how far it is from 180. So cosine of 30 degrees is square root 3 over 2. And since it's in quadrant 3, it'll have to be negative. So this is going to simplify to negative 3 root 3. The 6 over 2 cancels out to 3. For my y value, 210 has a reference of 30, so sine of 30 is 1/2. But since we're actually in quadrant 3, it's going to be a negative. So this simplifies to negative 3. So for my final answer here, I get negative 3 root 3 comma negative 3. And you want to make sure you write it as a point, because I'm looking for the rectangular coordinate, so I want it as an xy point. So really this should not feel very different from 5.4. It's just we're doing something, like we're using it for a different reason, but same formulas and same like kind of solution steps. Let's do part B together. So part B, I'm asking for polar coordinates, so that means I'm looking for r theta. So I must be being given xy. You're either being given xy or r and theta, and you're going to be asked for the other, the other one of them. Okay. So my equations for r just uses Pythagorean theorem, and maybe we should graph it first. I always kind of forget to do that, but it really is good to do it. I don't worry too much about placement and stuff like that when I graph. I really just want to know what quadrant it's supposed to be in. Because for instance, with part A, 210 being in quadrant 3 made sense that both my x and my y should both be negative. This one, I have a positive x, negative y. That's going to put me in quadrant 4. So that means that I should get an angle in quadrant 4. So I really just use the the graphing part to help me know like what quadrant I'm in. So r is the square root x squared plus y squared. So I'm plugging in all my stuff. I get square root of 3 squared plus negative 1 squared. Square root of 3 squared is just 3. 1 squared is just 1. So I get square root of 4, which is 2. So my r is 2. Then I can go get theta. Now, with theta, I can use a few different trig functions to go get it. I can use sine, cosine, or tangent. Here's where we have to be careful though. If we use cosine for this, it's going to give us an answer in quadrant 1. and we're going to have to force it to be in quadrant 4. Now, that's not too bad whenever you don't have to use a calculator, but sometimes we might want to keep that in mind. Like if you are using a calculator or not. I'll show you what I mean. So for my equation, so I can use basically any of these. I can either use the fact that tangent inverse is y over x, so negative 1 over root 3. I can use that. I can use theta equals sine inverse and say it's the y value over the r value, so that's negative 1 over 2. Or if we want to, we can use cosine inverse, which is going to say square root 3 over 2, which is the x over the 2, over the r. So I can use either one of these, but I only have one correct answer. The problem is your calculator is going to give different answers for some of these if you use a calculator. Now, I don't believe that you need to. I think you can just look at the table for this one and say, okay, so I have my sine, cosine, and tangent, 30, 45, 60, 1 over 2, root 2 over 2, root 3 over 2. I'm writing this down real quickly. So this was my table. So what does it look like? What should my angle be? It's definitely looking like 30. Because I'm seeing, okay, tangent is 1 over root 3. Cosine is root 3 over 2. Sine is 1 over 2. You don't need all three of these. I'm just showing you that any of them could have worked. The issue is going to happen if you use your calculator. And then also we need to be careful because this just has a reference of 30 degrees. Theta is not actually 30 degrees. Theta is 330 degrees because we would have to do 360 minus 30 and get 330. If you type these in the calculator, you got to be careful. The issue is that this one's going to tell you 30 degrees. This one is going to tell you negative 30, and this one's going to tell you negative 30. But we almost never want to leave our answer with negative degrees or negative radians, so we would want to find the positive angle. Really, my point here, I feel like I gave a longer explanation than needed, is that you're going to have to be careful about the quadrant of your theta. So keep that in mind when you're picking like which trig function to use. And so I want to do another one of these where maybe we have to use a calculator just to show you, how it can maybe get a little tricky. So this one is negative 3/6 into polar coordinates. And for this one, I'm going to say leave the r exact, round theta nearest 10th of degree. So for this one, a very similar idea. We're looking for r theta. We're being given x and y. This one, I have a negative x and a positive y, so that's going to put me somewhere in quadrant 2. So r is square root negative 3 squared plus 6 squared. So I get 9 plus 36, which gives me 45. I'm fine if you left it at 45. However, my math lab is going to ask you to reduce that. So it'd be 9 times 5. Square root of 9 is 3. So this becomes 3 root 5. And now for my theta. Now because I need to use the calculator, I need to be a little picky about which one I use, whether I use sine, tangent, or cosine. Cosine is the only one that can give me an answer in quadrant 2. So I'm going to use cosine inverse for this one. So cosine inverse is x over r, and I'm choosing cosine inverse because it's the only one that gives excuse me, I just sneezed and oh, sorry. I tried to mute myself just now when I sneezed and I did not succeed. So I am so sorry if that was like loud. Oh my gosh. Okay, what was I saying? Oh, I got off track as I sneezed. Choosing cosine inverse because it's the only one that gives an angle in quadrant 2. Now the reasoning for that goes all the way back to 4.1. So if you need to remember like which inverse function gives answers in which quadrant, I would go back to 4.1. But I'm going to plug this one in. So I get -3 over 3 root 5, or you could write 45, whichever one you like. And so if you plug this in, be careful here. Just now when I plugged it in, I needed an extra parentheses around my denominator. It told me domain error, and I was like, well, that's not right. So make sure you keep a parentheses around that denominator. If you just type in square root of 45, you don't need the extra parentheses, but just be careful. Your answer here is 116.6 degrees. So my final answer for this one is 3 root 5, comma 116.6. And again, if you just wrote it as root 45 instead of 3 root 5, that is okay with me. It's really not a big deal. If you want to remember like which trig functions are helpful in which quadrants, I did talk about it a bit more in 5.4. I'm going to scroll up real quick and show you what I'm talking about. Where did I write it? Here. When looking for theta, I would use tangent for all of them, pretty much except for quadrant 2. And if you're in quadrant 3, you're going to have to add 180. And so I would actually use the same information that I gave up here. So I'm actually just going to copy it. And I mean, again, you don't have to do it this way. This is just a way that I've kind of condensed maybe what is most efficient to sort of help give you some guidance. So let me go ahead and write that down here. Hello. Paste. There we go. The only difference is that instead of this like Vy, Vx, and all that kind of stuff, I just have like X, Y, and R. I don't have the V in front of it because I'm not dealing with vectors. So this really is not any different. I'm using all the same formulas. I just changed them a little tiny bit because we are working a little differently, like what our goal is. So tangent is y over x, cosine would be x over r, tangent y over x, tangent y over x. And that's it. So you'll just have to be careful whenever you're looking for a theta, and it's really just because of the quadrants. Sometimes they can get a little bit tricky. A little bit tricky. I just want to talk a little bit too about the purpose of polar coordinates. If you are an engineering and science major, you will get a little bit further in polar coordinates as you go up. We won't do anything crazy with them in here. We're pretty much just what I've shown you so far is my expectation for you on the test. But what really they're used for is graphing like cool stuff. So shapes like this is like a clover shape. This has to use polar coordinates to make a shape like that. X, Y points can't do it. Or shapes like this. I don't know if you've ever seen this one before. This is the spiral or the golden ratio. The golden ratio is super cool. If you look it up, it's just in a bunch of stuff that we see like in nature and stuff like that, like the shell of like a or like a snail, or there's like a bunch of stuff in the ocean and stuff like that that has that shape, or um, it actually follows, it's very closely related to Fibonacci numbers, if you've ever seen that, which like pine cones, the ratio of the pine cones or what, or they follow the Fibonacci sequence. Really cool stuff. Is really what you can get into, like if you look some of that stuff up. It really is cool, and it's probably one of my favorite things about math is the Fibonacci sequence and the golden ratio, just because it just like pops up in our world and it's super pretty and cool to look at. So that's just some like kind of where polar coordinates would like lead you to, is graphing stuff like this, but we won't really get into that, but I just wanted to show it to you. So this is actually it for 6.4. So really all that I will be expecting you to do is be able to convert between rectangular and polar coordinates. And it is, of course, good to know how to graph them so that you can be able to check your quadrant and stuff as you're solving. So as always, if you have any questions, please reach out to me. I can always meet with you on Zoom or in person or anything if you're in the area. But I hope you have a good day, and I will see you in the next video. Bye-bye.